So this week is all about regressions. So this is kind of putting together everything we've looked at before, especially the first few weeks are about the kind of basic concepts and the terms and stuff that I'm going to be using, so I should assume you know that. And the next weeks are about RCTs, and this is kind of what happens when you don't have an RCT to use. I mean, how do you kind of answer the same questions, and what mechanically you're using. And what we're actually using is a regression analysis. So this is kind of the idea. Let's look more at the big picture about what a regression is, what we're going to be doing with it, a little bit of motivation with where this is used before, the kind of the power of it and why it's so important that we understand what people mean and that we get it right. And then we'll go over some of the basics. And when I say basics, I mean basics, but I also mean fundamentals. And these are the things that, in essence, every other kind of course you do on regression analysis will just expand upon these. Basically, so the big picture. So why would you use regression as a tool, whatever regression you've done here? So you would use it, and there's actually three reasons. Let me put here two, because these are perhaps the two most interesting. Either to predict a variable, so if I want to know what employment it's going to be in a year's time, I might use this. Or to find the causal effect of one variable on another. So I want to find, if I increase the minimum wage, what is the effect this is going to have on employment? So these are two very important, very interesting questions that are going to have big ramifications, depending on what the answer is. So in this particular course, we're more interested in the latter. I think that has more interesting techniques about it, but we're going to talk about the first as well. And the third one that I haven't written here, and which is actually the one that you probably come into contact with the most, is kind of more as a descriptive measure. So you have descriptive statistics where you write down like a table and there's 30% of the population are male or whatever. You can use a regression to get more of a descriptive analysis of the data as well. If you're not particularly, if you're not confident to say that you've achieved one of these two things, which in reality you're never going to be 100% confident on that. So yes, this is of course more interesting than the latter. But to kind of frame the discussion, we have a question. So, what does a degree does a degree at LSE give you better career prospects? So we don't have an RCT to answer this with. In previous classes we've gone over what RCT is. So if we randomly assigned treatment being if you went to LSE or not, then great, we would be able to answer this question nicely in that context. But of course we don't have that. LSE is not going to randomly give out places, although it does seem like that a little bit sometimes. But that's a little bit of an aside. LSE is ridiculous for that. It has the most applicants per place, but it doesn't do anything other than basic A-level results. Who knows how they decide conditional on the A-levels. But anyway, so here's an answer. Econ graduates from LSE earn 34,000, Econ graduates from other universities earn on average 26,000. Big difference between this, so the answer is yes. Assuming that I mean by career prospects, I mean better salary, right? So, the question I put to you is why might this not be the answer? Yeah.
There are a lot of other variables that people who have LSE econ degrees might be very different from those who have econ degrees from other places.
Precisely. So people from doing LSE, doing econ at LSE, by definition, probably live in London. London wages are higher, they're more likely to then want to work in London, so more likely to get higher wages. As one example, perhaps not even the most convincing example, perhaps the most convincing example is that people that go to LSE have a certain background. Whether that is having achieved higher in tests, and not that that has that means that they're more intelligent, but it perhaps has a correlation, or at least a correlation with their ability to do well in tests, which are an important thing in the workplace as well. So, looking at this, we can't actually tell the answer to this question. And in fact, there have been loads of studies done on private schools, and whether sending your child to a private school means that they'll have better career prospects, and career prospects, where economists we like numbers, we mean higher income. And although these are very, very difficult and the results are very controversial, the general consensus is, actually doesn't matter. You can send your child to a state school or to a private school. What matters is the fact that your child could have gone to a private school, i.e. has a rich family background, is more likely to have been read to when they were younger, etc., and have the connections with their family. So what we've talked about is something called selection bias. We're not comparing like for like. What we really want to do in this question is send someone to LSE and then look at what happens if we send the same person to a different university, say Swansea, to do economics. Obviously we can't do that because you only go to one university. And we'd like to compare the person that went to both but didn't go to the other and see their difference, but obviously not such a person exists. So, yes, so to answer this question, you'd like to observe the same individual. Yeah, okay. So this is impossible. So, but what we've discussed very briefly here is a few variables that we think are skewing our results, such as high family income, maybe even a high proportion of people coming from overseas. So we could plausibly, once we've controlled these, once we remove them from the equation, and we know all of the things that have this biasing effect, then we could compare like for like, and we could get an idea of the estimate. And this is kind of approximating an RCT in a sense. But of course, sorry, I've got a bit of a cold. But yeah, two issues. How do we know when we've got all the things we want to control? The answer is we don't. You never do. You can control for as many things as you think, or the most important things. And this is where thinking of things in a kind of economic thought process is very useful, and your intuition behind it. And we don't know for sure when we've got them. And in fact, it was probably impossible. There are many, many things that impact this that you can't observe. But in this course, we're more interested in, so this is an economics course answering this question. This is more of a statistical econometrics course. How do we actually go about controlling things? And this is where regressions come. What is the actual, like I've said controlling, oh, we want to control this. What does that actually mean? And that's what we're going to cover, or go into this week, but cover next week as well. But before we do that, it's a little bit of motivation as to where regressions are used, the importance of regressions, and the importance also of getting it right, of understanding what is happening, and making sure that you understand what's happening in papers and things, so you don't get them to the wrong conclusions. Because these can, as we will see in these, reach far-reaching conclusions, which may be controversial. So, I don't know if anyone does law and has heard of the Kleski versus Kemp case in 1987. But this was in the USA. Warren McCleskey was convicted of armed robbery and murder of a white police officer. He was sentenced to death. But this guy called Bladus did a study, and he found that in the US justice system, if you killed a white person as compared to anyone else, you're 4.3 times more likely to be sentenced to death. So what Bladus has done here is he's shown statistically, using regression techniques, that the US justice system, at least in the 80s, was racist, institutionally racist. I mean, that might not come as a surprise to a lot of people, but now we have solid hard evidence of it. And what makes this case more interesting is that, and why it's called like a landmark case, is because the judge rejected this evidence. Because this isn't evidence about averages, about things that happen on average. It's not about individuals. So the judge said, no, we can't take this into account, the fact that we are, on average, 4.3 times more likely to convict this man. We've just got to look at the individual things. which is perhaps an interesting kind of facet of it. So, secondly, we're going to talk a bit about this man called Galton. Galton is considered the father of regression. He did the first ever regression. And we're going to do it again in a minute. History in the making. Galton was interested in peas. He was interested in peas because he was interested in hereditary traits and genetics. He wanted to know if my traits are passed down to my children, and in animals and plants as well. And to what extent they are. Now, why did Galton want to know this? He wants to know this because he was a staunch supporter of eugenics. He was a massive fan of them, and his thought process was that if I can prove that desirable traits are handed down through generations, then I will have evidence to support eugenics, and that we should use eugenics. Perhaps not the nicest of man by our standards. So Galton got a load of peas, and he measured the weights from the mother plant of the peas and the weights from the child plant of the peas. And his hypothesis was that they would be related. And then we could say that, okay, so if the mother has heavier peas, and this means the child has heavier peas, and the mother is passing down some traits. Why did he choose peas? In the first example of good research design, Galton realized that normally you have a man and a female, and you're going to have to look at the traits of both when you're looking at their offspring. But the peas he used reproduce asexually, so you only have to look at the females. Great. And Galton found that there was a relationship, and it was a solid relationship, that the weight of the mother's peas did affect the weight of the offspring peas. He found this, and he was like, great, evidence that we should use eugenics, go and tell everyone, eugenics are a great thing. So, two cases that we very quickly covered. One shows that the US justice system is institutionally racist, at least in the 90s, and the other supported eugenics, at least in the eyes of this guy. So, what this shows is A, regressions are used an awful lot outside of economics, and B, they're used to create devastating conclusions. And it's really important that we can analyze exactly what was going on in these two studies to make sure that they've got it right. I mean, Galton's study was right, perhaps his conclusions were not, but yeah, so it's important that we know what exactly is going on. So, onto the mechanics, the actual what is happening. And there is some maths we've got to know. This is it. And I hope I'm not patronizing anyone here, but I'm just going to give it 0.5 times mother's weight plus some constant. And if we trace this down, you can see that's about 4. So great. We've done it. And then this is kind of in words what we were saying before. So we have a theoretical model in our head, what we think the world looks like. And the important difference here is the error term. Now the error term is something that if you do any kind of thermal courses, you'll study a lot. But we're not going to talk about it that much here. What this means is that we don't think that you can determine offspring weight exactly by the weight of the mother. If the mother's weight is 2, we don't think that there's a universal rule which says offspring weight is going to be twice mother's weight. We think that on average it's going to be equal to some relationship between mother's weight and offspring weight, but there's going to be an error term in each one. So if the offspring weight equals 3, say alpha equals 1, and say beta equals 1, then offspring weight equals 3 and mother's weight equals 1. We have 3 equals 1 and 1 times 1, so the error term in that case is 1. So we don't think that this is true exactly. There's going to be some kind of error in it. So we have this idea, this model in our heads first of all, we think it, and we think this seems reasonable. Then we write it down in a kind of mathematical form. And then we get the data. We get this. And from this, we can estimate these two coefficients here by looking at the intercepts and the slope. And then we have a realization of our model from our sample, and and then we have an idea of how these two variables are related. So that's all well and good, but I haven't talked at all about how we drew this line. In this example, it seemed quite obvious, right? But it won't always be the case, and the inferences that we draw, reach, having drawn this line, is kind of everything, right? We have the slope coefficient and from that line we get the 0.5, and that is our evidence for eugenics, the support of it. So we really want to be confident that we've drawn this line correctly, this line of best fit. And the question is, how do we do that? If we have data that looks a bit like this, then drawing a straight line on that might, a line maybe through there, might seem nonsensical. Maybe we should draw something more like this, and this, to people who don't know, is kind of like an exponential relationship. And maybe then our model, which was based on equation of a straight line, is wrong, i.e. our model shouldn't be linear. What happens if we have data that looks like this? How do we draw the line of best fit there? Maybe there isn't really a relationship there, but we'll go on to that a bit later. And then we have this one. Now, I thought we could do a little exercise here, which is, you always have the lecture notes, so you will have a picture of this. What I want you to do is to draw a line of best fit on it. But remember how important this line is. So don't just draw it willy-nilly. I'm going to have some kind of rule in your head as to why you've drawn it. Maybe you've connected the first and the last dots, that's fine. Maybe you've just connected the dots. Although, remember that we're thinking of things in terms of this kind of model. So preferably draw something that's a straight line, but you don't have to. You don't think that works. So when you've got some rule, that's fine. And I can have a drink while you do it. So, does everyone have a go? No, I don't know any names other than Alex. Well, I don't know any names. But, I don't know, Alex, do you want to share with us what your rule was?
Okay, so my rule was just to approximate a similar distance between the line and the dots on both sides.
Okay. So, as in, like, if I drew a line like this, it'd be this distance here and here.
Yeah, but then aggregate it so it's the distances of between the dots and the line underneath, and the dots above and the line.
Okay, and try to add them up to the same. These ones and these ones.
Yeah.
Okay, that's a pretty good shot. Yeah. Anyone else do something different? Yeah.
Okay, I don't know. I guess maybe I misunderstood, but I thought we had to have a straight line.
Yeah.
So with a straight, like, since they kind of look straight, I tried to have the same amount of dots at both sides of the line, while also making it look in the middle. So then I was going to draw it so that it went straight through those two middle lines, two middle dots.
You could just draw it.
Yeah, I can just show it. So I thought I'd draw it so that it would like go through these two. But I realized that these ones were significantly further away than these three bottom ones.
Right, yeah.
So then I kind of just did it a tiny bit up from these two.
Okay, so you're something a bit like
Yeah.
like this.
And I realized that would be like 0.5x plus 3 more or less. Well, at least on my page.
Okay,
it
yeah,
ended up
yeah,
being
Okay, cool. Does anyone else have anything
Oh.
on that?
Mine curved.
Your curve? Yeah, no, that's fine. Yeah.
It looked curvy.
Yeah. So you had something like this.
It curved and like every point was either pretty much on the line or pretty much the same, on average the same distance away from the line.
Oh yeah. So kind of a general theme is keeping these distances kind of on average the same, right? That was kind of seems like a reasonable way of doing it. Yeah. So that's like exactly what people do. You guys have just invented ordinary least squares estimation, which is, well done. Which is the estimation technique that is most widely used, and is probably what you'll see in papers. I mean, a lot of fancy words are just kind of different versions of this. They're doing different scenarios. I mean, as I said at the top, there is no exactly correct answer in all cases. Different cases will require different methods. If you've got something that doesn't look linear, like we had before, don't draw a straight line on it. There's going to be a different way of doing it. But yeah, so this method is called ordinary least squares, or just least squares estimation. We quite like it at LSE because it makes the acronym LSE. But yeah, so the idea is you draw a line so that you've minimized these distances, the sum of the dots. And this is the best fit to the data of your line. So that's great. We have now an idea of how to draw, and now perhaps you can see why I picked this data exactly how it was. It's because these things are the same, and it goes through the middle three. So that was a very easy line to draw. But in fact, you can get Excel to draw this line for you. And what you've done by calculating these distances and then fitting this line is, as I said, ordinary least squares estimation. It's got a kind of semi-complicated formula, but statistical packages will do it for you, so there's no particular need to worry about that. What's important is that there is a rule, a method of getting this line in the right place. And that's very important because we know that the inference is based on this line. And remember, this line is just fitting the model to the data. Inference is based on this line is very important and far-reaching. But there's more to it than just the line, right? So far we talked about having a model, getting data, fitting a line to the data, and then we get these estimates in this regression formula. We run a regression, we get the OLS, ordinary least squares estimates, these. Great. But in these two diagrams, it may not seem it because the scale is different, but the slope is exactly the same. I have the same points of data and the slope is the same. But my question is, are you as confident about this slope being correct, being representative of the data, or about this slope being representative of the data? And the answer is, okay, yeah, this one is quite good. If this was my model, was a linear relationship, I got this data, I ran it, I found this, then I could extrapolate this to the population. On this one, nah. If someone showed me this diagram, I would be very skeptical of their results. Although the slope is 0.5 on both of them, we have a lot less confidence that our model and our realization of the model actually is reality. And why do we have that less confidence? Is because this data is far more spread out than this. So this is all nicely around, upwards trend, great. This is far more spread out. And how spread out the data is the variance of the data. It's called variance. And I think you went over that in the first few weeks. In econometrics, in studies, you'll see something called the standard error, which is basically just the square root of the variance. It doesn't really matter what it is, because all you need to know, or what you need to know in order to understand it, is that it's a measure of how varied the data is. And we get these standard errors, and then the things you see in regression tables and brackets underneath the point estimates. Because if the data is too varied, if the standard error is too large, then we won't have any confidence in this line being representative, i.e. that the slope of the line is different from 0. As a rule of thumb, if the standard errors is more than half of your point estimate, so if you estimate beta as 1 and your standard error is 0.6, then your data is too spread out for you to make a valid conclusion. Now obviously, there's going to be another variable at play here, which is how many data points you have. Because if you only have 2 data points on a graph that looks like this, I draw a line of best fit, minimizing the distance, but it's just going to be one that connects them, right? Then, and I've got, oh, this is, beta is 10. No one's going to believe that. You've only got 2 data points and you want to extrapolate that to the population? No. So another thing that takes into this useful, well, that's needed to know here is your sample size. And that's incorporated in these things called the standard errors. So this is variance and standard errors. This is this, but without the line. And if I showed you this and asked you, is there any relationship between the x variable and the y variable? You'd probably say no, right? I mean, no. So it's useful to point out here that you can always draw a line of best fit, i.e. you can always run a regression of 2 variables. Whether you should or whether it makes sense is something else entirely. And the answer may be no, as it is here. So we talked about drawing the line, i.e. running a regression. So you have a model, you get the data, you run a regression, you draw your line, you get a measure of how varied the data is, which will give you an indication of how confident you are that your line is correct, or that your line is representative of the population. But you may also be interested in something else, and that is how much of the variation in your dependent variable can you explain by your independent variable. Now what I mean by that is, if we had a rule in nature that was the height of your height is twice the height of your dad, then using the height of your dad, you'd be able to explain your height 100%. Entirely. If that was a steadfast rule, we would be able to know the height of anyone's child just by looking at their father. 100% true. And in that case, your independent variable, height of your father, explains 100% of the height of your child. Its explanatory power is 100%. We've got everything. But we know that's not true. We know that in reality, the height of your father and your mother and your parents together does explain your height to a certain extent. If my parents are 7 foot, I have more chance of being above 6 foot than if my parents are both 5 foot. But we don't know for sure. There are anomalies. There are people that have different things. And what affects their different things with people and heights? Maybe it's genetic mutations, but maybe it's also nutrition you receive. And in terms of going back to the P example, it might be that when Galton sent his P's off to all of his students and friends, some of them might have been great horticulturists, great gardeners, and tended to them really well, giving them lots of water, lots of nutrition, and therefore, the offspring of their peas might have grown larger, and they might have produced heavier peas. And then some people he might have given to, and they might have just forgotten about them after they've planted them, not bothered watering, etc. They have no idea what the right nitrates or whatever are, or maybe they just had the wrong sort of soil where they were. So these things are going to have an impact on the weight of the offspring. So the question is, how much of an impact do these other things have that we haven't included in our model of how the world works? And that is, by the way, why our model has an error term. It's kind of us saying, oh, and there are other things in there. This makes it correct. Yeah, but yeah, there are other things. But how much of the variation here can we explain by this is then obviously very important. So if the answer is not very much, then this is not a very good model of how the world actually works. If the answer is a lot, then maybe it's quite a good model. Now, in terms of bivariate regressions, i.e. regressions with two variables, which is what we've been doing the whole of today, and is what this is, the explanatory power of your model is going to be closely related to the confidence in the slope parameter you have, i.e. how much variance there is in the data. When we go on next week to discussing multivariate models, i.e. ones with many explanatory variables, we're going to find that the relationship is not so obvious. And thinking now, it's quite obvious that this model, in general, with only two variables, is not going to be a very good representation of the world. We don't, in general, think that any one variable of interest, whether it's the weight of offspring P's or whether it's employment or income or whatever, we don't in general think that it's just dependent on one variable. So we're going to want those ones. So, but in the bivariate case, there is definitely a relation. So if we go back to this, what we had here, this model has an explanatory power of 0.7, i.e. 70%, and this one of 0.1. And that makes a lot of sense, right? We think that this number, the weight of parents, has much more explanatory power on the weight of offspring here than it does over here. And what in economic studies and econometrics, we call this explanatory power the R squared, which has a fancy formula, which is about the explained sum of squares and the residual sum of squares, which are the differences that we can explain and the differences we can't. But again, so long as you understand what it is intuitively, it's not important to the formula, because it's all done for you by fancy computers. Yes?
What does the number mean? Like when you said 0.7 explanatory power, like, okay, so that's how you work it out, but what does that actually mean?
So that means that 70% of the variance in our dependent variable, of the differences we see in our dependent variable, it can be accounted for, can be explained by our independent variable. So if that was low, then we wouldn't be able to use our independent variable as a good predictor of our dependent variable, because there's lots of uncertainty then surrounding it. Yes, so in this diagram, the explanatory power is much larger, and in this, it's much lower. Okay, so we have now kind of the whole story. We had a model. We thought that some dependent variable, sorry, I always get those mixed up, some dependent variable, and we think that some independent variable affects it, so we might think, going back to our example right at the beginning of an LSE education gets you better career prospects, then we might think career prospects, which is just obviously income, because that's all we care about in a career is our salary. And then we might use as our x variable something called a dummy variable, which we'll talk about a lot more next week, which is whether you've been to LSE or not. So this variable will just be a 1 if we went to LSE, or a 0 if we didn't go to LSE. And then so our hypothesis, our model, is that there's a relationship between these two, which is that beta, the slope parameter, is greater than 0. So I'm thinking, okay, I think that if you've been to LSE, you're likely to have a larger salary. We talked right at the beginning why it might be the case that actually the effect of LSE itself is confounded by all these other variables. And we'll talk about that next week when we include more variables here. So we might have beta 1 there plus beta 2 x2, and this might be your family income, etc., etc. But at the moment, we're ignoring this, and we're just having a model like this. So all of those things are captured in our error at the moment. So we have a model like this. Okay, great. Then I go and I survey all the recent LSE graduates, and I survey a load of graduates from elsewhere, and I get their income. And then I make a line on it by using LS, and I get a estimate. I get a realization, and then I also get an idea of the variance, how spread out my data is. So we have get the standard error, which is normally reported in brackets underneath. So that's 1, 0.1. Fine. That's low enough. Am I happy? Yes.
Sorry, I'm just confused because if there's a dummy variable that was either 0
Yeah.
or 1, wouldn't that mean that there, like on the x-axis, there'd only be 2 lines?
Yeah.
Why is there a spread?
Yeah, so that's a very good question, and that's because it was a bad example. You're right. Okay. Yeah, let's call this Z to differentiate it, and we'll go back to the P's. Okay, so this is weight of, these are 2 continuous variables. Yes, sorry, you're very right. These are 2 continuous variables, and we have the data, and we draw a line. Okay, yeah. So we have the data, we have some sample, we do OLS, and this is when we run the regression. This is when we theorize. This is when we run the regression, and this is our results. And we could say that the standard error of beta 1 is equal to 1.1. Kind of how we would notate it, whatever the word is. And then we would we would then have a look at the R squared, see what the expansion power of this is. Say it's 0.54. Okay, so we explain 54% of variation. Fine, whatever. Can't really expect for much more. In fact, that's excellent because you've only got one variable here. So yeah, so we have a model, we get the data, we do the regression, we get the results. We have an idea of how confident we are in this number and of the expansion power of the whole model. And that's kind of all we've done. So I have a sense of the usefulness and the importance of regression, how often it's used, and what incredibly large conclusions can be drawn from it, large and perhaps sometimes worrying, and why it's good to be able to critically analyze And we've understood the basic, how mechanically a regression is done, drawing a line of best fit in the two-dimensional bivariate sense that we've done at the moment. What slope coefficient means, we've understood the variance importance, the exponential power importance. Next week, we'll come back to causality, because we've kind of left that behind a little bit by talking about the, the mechanical properties. And go to multivariate regression. So obviously when I have 3 variables, it's going to get difficult to draw, and when I have 4, it's going to be impossible. So the reason why we've done 2 variables, a bivariate case first, is because the intuition behind all of this, where everything comes from, is exactly the same when you add more variables. You just can't really visualize them, but it's exactly the same. So all of the concepts we've covered here, just going to be covering again, basically. And that's kind of, in reality, it all boils down to nothing really any more complicated than this. But yeah, things can seem. Yes?
Going back to your bad example, but we're trying to sweep under the rug.
My bad example, yes.
Yeah, does that mean that it's not appropriate to run a regression analysis on a dummy variable?
No. It's perhaps when you only have a dummy variable on the right-hand side, then you're probably going to want to look at doing things other than these things. Can you help me out?
Yeah, I was just going to draw what it looks like in a dummy variable, just kind of really show what it would be. So I guess in a dummy variable, what you'd have is, if you go to the LSE income example, I'm just going to represent y as the income, so you have income here, and then you'd have LSE. Yeah, okay, this is not great. Imagine for some reason 0 is here, right, and 1 is here. So let's say a hypothesis is that we expect, in reality, people have lower income who don't go to LSE, so you'd have a lot of x's here. And with the 1s, you'd have a lot of x's here. And you still minimize the distance, so it'd be maybe something like this. And you're still minimizing the distance, it's just that all the points just happen to right. So you can do it, but yeah, and as you were saying, in most cases, when you just have 2 variables, it doesn't really much as meaningful.
Yeah, so, okay.